Thank you, Vincent, and good afternoon, everyone. And I'm Yuanbao Lin. Today, my topic is about the enhanced performance of the stability of the OPV by interface of photoactive layer engineering. And this is my contents today. As we know now, now the we because we spend lots of gas and oil in recently, especially with a rapid development of the economy. So now we development the PV technology and OPV and postcard as a third generation of OPV attract lots of attention recently. And especially in UK, we can see the cost of the gas and the electricity is 3-4 times as compared to before. So it's very urgent to develop the new PV technologies. And why we use the organic soil cell? Because organic soil have a now high performance now. We can get the 90% and with some kernel resistance, and the highest performance now is 90.2 from the MDO's data. And also the organic soil cell is stable with some polymers acceptor. We can the OPV can survive over 10 years in the South China, and also we can use the printable techniques to propagate the large area and flexible organic soil cell. And also the OPV, because it's thin and flexible, so it can have some potential application like the flexible OPV in with compared to the OECD or semi-transparent OPV with some greenhouse or indoor solar cells. This is the standard structure of the organic soil cell. It contains ITO, hot transfer layer, and photoactive layer, and electron transfer layer. But for hot transfer layer, we always use PEDOT PSS for the standard structure and moly oxide for the infrastructure. There only this majorly we use these two. So, but as compared to the photoactive layer or electron transfer, limit choice of the hot transfer layer in the OPVs. And for PEDOT PS, they have some drawbacks of PEDOT PS because it's high acid material. So after the several times, the ITO will be degradation and the stability will be it's not good for the device stability. And also for the PEDOT PS, it also some visible and the near MI wavelength, so we lost the light in the photoactive layer. So we need to declare the hot transfer material for the OPVs. So my first project in house is use the sonication to obtain the 2D material nanosheets. We choose tungsten serval and molybdenum servals. And from the high resolution TM, the tungsten serval suspension nanopad have a very clearly crystallized structure, but for the molybdenum oxide, this structure is not obvious. This should be because the multi-layer stacking of this MOS2 after the sonication. And then we try to sprinkle this 2D material suspension on the ITO. And from the EDS mapping, the coverage of the tungsten serval is comparable to the ITO, but for MOS2, we can see some dark area. It means the poor coverage on the ITO. And we test to the one of the highest performance in the 2019, the PM6Y6 and PCPN. And we get the higher performance as compared to a PEDOT PS because of the increase of the photocurrent and also the view better, but slightly reduce the VOCs. The enhanced photocurrent is because of the more photo response in this wavelength. This is because the PEDOT PS absorbs some light in the visible light and the MIR region. So when we use the 2D material, we can increase the photo response in this wavelength. And this work was published in the 2019 and was highlighted for the Nature Energy journals. But why I didn't continue with the 2D material because this suspension is unstable. You need to store it in the low temperature. Otherwise, the 2D material nanobread will grade again, and we can see some powders in the bottoms. And in 2019, in the post-sky solar cell, the two pad is used is synthesized and used to replace the PTAA. And these two pads same have a better performance and better stability as compared to the PTAA. So we try to use these two pads same in the OPV, and we spin coating on the two pads same on the ITO, and we use SPS. We can detect the two pads on the ITO, but due to the thin layer of the two pads on ITO, so we can detect a high ITO also. But from FM, we can see any difference after spin coating the two pads on the ITO. This because the interesting layer of the this material. But from EDS mapping, you can see the distribution of the two paths is very homogeneous as compared to the ITO and PEDOT PSS. And also from absorption, the two paths absorb less light as compared to the PEDOT PSS after 500 nanometer, which will benefit for the photoactive layer. And from the energy level, because these two paths have the work function of around 5.3, which will increase the hole ejection efficiencies. And when we test the hole only device, and the hole mobility is a little bit enhanced as compared to the PWS. And also these 2% have a different surface energy and the wettability as compared to the PWS. So when we spin coating the bulk heterojunction on two pad, we can see the nanofibrous structure. This nanofibrous structure is is better for the charge changeable, but for the active layer on the PWS, it's very hard to distinguish these nanofibrous structures. So in the performance, we choose another high system like PM6BTEC9 and PCBM10 systems. And as a result, the photo current and field vector is slightly improved as compared to the PTOPS. And this device we can get 80% performance, but slightly decrease the open circuit voltage. And this work was published in 2020 and achieves over 300 citations now. Also for the stability, these two pads have a higher stability as compared to the PTOPS. This because we use the EIS to detect the flash device and the edge device. This because the interface resistance of the same based device is more stable as compared to the PTOPS. This should be the PTOPS is acid material, so it will make the degradation of the ITO during the aging test. And also we must keep checking the work function of the ITO2 pads, ITO SEMs, and ITO PSS. The ITO SEM is more stable than the ITO PSS. And also we try to recycle the ITO substrate after the testing, and reuse the ITO again and again, and after 3 times, the PWSS, the ITO will be degraded a lot from the 70% to 30%, but for the same base one, it only degrades a little bit, 1% only. And this because after recycle, the ITO SEMs is the morphology didn't change, but for the PWS, we can see the morphology change a lot. This also I mentioned before, the degradation of the ITO size. But we also notice the VOC of the ITO2 pass SEM based on device is the VOC slightly lower than the PWS. So we try to synthesize the new one with different angle like the fluorine, bromide, and MEO. And with different angle, the work function and energy level change a lot. For example, for the bromide 2 pass, the work function can go to the 5.8, but for the MEO 2 pass, the work function reduced to 4.6. So we choose these 3 material to test in the OPV. As we can see, the MEO2 pass due to the lower work function, and the VOC is reduce a lot as compared to a PEDOT. But for the bromide two-pass, the VOC is better than the PEDOT. And finally, you can get a higher performance without sacrificing the VOC and also maintaining the JSC and view vectors. And also, these two-pass have lots of lots of people use these two-pass now. For example, they can put the two-pass in the bulk heterojunction solution. And after spin coating, this two-pass can self-organize to the ITO size. And also they can combine the ITO two-pass and the bulk heterojunction two-pass and use the indoors solar cell, and they can get the very high PCE. And also because this two-pass is very thin, so for the transparent, this system is more suitable for the transparent OPV device. However, when we compare the lifetime of the two-pass, it's increased as compared to a PEDOT. But if we compare to the moly oxide, the TAT lifetime is still lower than the PEDOT or still lower than the moly oxide. But for the infrastructure, the infrastructure performance is lower than the normal structure. So in my another work, I try to put the bromide two-pass solution between the bulk junction and moly oxide. We call it hybrid bromide moly oxide because this one is we cannot determine is the self-assembled monolayers. So we call this one a hybrid moly oxide and bromide two-pass HTL. So as a result, the VOC slightly increased and also the view vector is slightly increased as compared to the only moly oxides. And also we test the lifetime of this material. As we can see, the TAT lifetime with a continuous measurement, it can increase around to 650 hours, and for annealing stability, it also increased a lot. So we try to use the toxins to detect the distribution of the donor and acceptor and the moly oxide in the OPV device. As you can see, the moly oxide after stability test, they will move to the photoactive layer. But with the bromide two-pass, it can partly block the moly oxide to diffusion to the photoactive layer. And also because the bromide two-pass can change the serval energies, and after the agitate, the distribution of the donor acceptor is more homogeneous as compared to the moly oxide based on device. Also, other group also try the two-pass, and with moly oxide also show the similar conclusion from us, increase the VOC and also increase the stabilities. Okay, I will introduce another work about the photoactive layer engineering in the OPV. And as we know, dopant is widely used in the organic semiconductor, like OLED and the transistor. But in 2019, we try to find out some dopants OPVs, and only three publications we can find for M-type dopant, but most of them is based on the P-type dopant. This is because the energy level of the M-type dopant is very high, so it's very easy to oxidize if we export in the air. So we try to synthesize some others efficient and low-cost M-type dopant. From the energy level angles, these two dopant can transfer the electron to the acceptors. And also the synthesis process is very easy as compared to the material synthesis. Only take 1 day to synthesize this material. And we try to add this dopant in the bulk junction, and after spin coating, we detect the enhanced EPR signal as compared to the without the dopant one. And also we also measure the absorption after the dopant. The low dopant, the absorption coefficient can increase a lot. But if we put too many dopant, the absorption coefficient will reduce. And also, this n-type dopant also act as the morphology modifier. If we add too many dopant, the morphology, the donor accept the best separation of the bulk-heterojunction will enhance. But if we add a little bit dopants, it's become more smooth and also more and also the crystal line, the pipette stacking crystal is enhanced with these dopants. And as the performance, at that time we tried the PM6 IT4F, and as a result, the low dopant can enhance the pupetta and photocurrents. But if we put too many dopant, the VOC, JC, and pupetta will decrease a lot. And also we tried other 5 bulk-heterojunction system, and all of them can increase a little bit with the tiny dopant. But if we put too many dopant, the performance all decrease. And also recently we tried this dopant with CL2%, and we get the 90%, 80.9% PCE. And also ternary is widely used to enhance the performance in the organic soil cell. And in last year, Feng Liu group in the Shanghai, they developed, use the nanofibers polymer donor. They can enhance the performance because they can form the more fibrous structure. So I'm wondering, could we find some fibrous morphology of the non-fluence acceptor? So I test different acceptor like PCB-MY6 and IDDIC. All of them have didn't have the fibrous structure. So we synthesize the ISO IDDICs, and this material after test with FM, we can see a very clearly fibrous structure. But if we test the BT9, because the YC series, they after annealing are very easy to upgrade. So we cannot see the fibrous structure in the BTC9. So we try to put this ISO DIC as the third component in the PM6 and BTEC9 system. And for the PM6 BT9, we can see the fibrous structure, but with the ISO ITTIC, this fibrous structure is more more clearly, and also we use it's more sharper and more clearly. And also we also get some pipette stacking order from GWAS data. The ternary can have a higher crystalline crystalline in the pipette stacking, and also increase a little bit in the llama stacking. But because the ISO IDTIC, the absorption is very close to the PM6. So in the binary PM6 ISO IDTIC, the PC only we got 1.7%. But if we add this one in the PM6 and BTC9, we can enhance to the 90%, which increase the view better, because the fibrous structure can enhance the charge chamber and also slightly increase the VOC. And in this one, because we also notice most of people when they choose the ternary system, the gas material, they always choose the high performance. But in this one, we demonstrate even for the low performance gas material, we also can get a high performance in the ternaries. And also we test the stability with these two. And we use the toxins. The ternary have a slightly enhanced stability compared to the binary. So we use a toxin to see the donor acceptor distribution in the edge and flash device. The binary one, after the stability test, the BTC9 will upgrade in the ITO size. But for the binary one, the distribution is more homogeneous as compared to the binary system. And also for the PM6, is very homogeneous. The distribution is more homogeneous as compared to the PM6 BTEC9 binary system. This because the isoisotope DIC have a suitable surface energy, and after this after adding this one as a third component, it can reduce a little bit of the acceptors surface energy. So we're partly enhance the homogeneous distribution of the donor acceptor after the aging test. And finally, I want to thank my supervisor Thomas, and also now a young micron group, and also my collaborator, and also the department and chemistry and power solar center. And thanks a lot.